So just for anyone who doesn't know, Dr. David Quesada is an associate professor with the Department of Psychology and Neuroscience and is part of the Computational Systems Biology Group at the Institute for Neuro-Immune Medicine. He holds a Ph.D. in physics from the University of Havana, Cuba, and an MS in physics and mathematics from Moscow State University. He's been in academia for more than 30 years in different roles and has started focusing more on biomedical problems in the last 8 years, and he joined the Institute team a year ago. He will present an ongoing project addressing the appearance of diabetes as a secondary disease of Gulf War illness, ME/CFS, long COVID, primary conditions. In the current phase, the goal has been to describe the response of the glucose-insulin feedback for a later integration with the cortisol HPA axis, HPG axis sex differences in immune responses. So without further ado, Dr. David Quesada.
Thank you, Makina, for the introduction. Okay, let me try to share my screen. Okay, share. Here you go. Okay, so the project is about the idea of simulating the progression of diabetes or the appearance of diabetes as a secondary condition. Basically, the tentative layout I have for today's presentations are the motivations and the statistical analysis supporting the hypothesis that we have for the modeling. Some ideas about the model construction, so how we build the model, and then from the model 1.0, how we could move to model 2.0 that will be more robust and better explaining some of the features and some of the statistical results that we obtained. So, but the project, the presentation today is more aimed at reporting about the ongoing process and asking for help to obtain medical data that might permit calibrate the results or discriminate mathematical representations, and getting any kind of feedback that might help to improve the idea that we developed for the model 1.0, just to create a model more robust that I will call the model 2.0. So what are the motivations that I have behind this? I got an article that was about the rate of chronic medical conditions for the Gulf War illness veterans, where one of the conditions that appeared with a lot of representation was diabetes and high blood pressure, high cholesterol. All these conditions are very related. And this analysis provided a comparison with the total population and how the incidence within the Gulf War illness people compared to the total population, you will get an excess of prevalence. As you can see, diabetes has a 5.4% prevalence in excess to the normal population. And for women, it represents an excess of 19.8. So it caught my attention why diabetes is appearing as a secondary condition to the Gulf War illness. And I started to dig in a little bit more on that. Later on, I was presented with data used in these two articles about the effect of the post-traumatic stress disorder on the Gulf War illness people, and also the post-traumatic with mild traumatic brain injury. So looking for regularities that might be associated with the presence of both post-traumatic stress disorder and mild traumatic brain injury. I continued digging into this problem, and I saw that even in post-COVID syndrome, diabetes is another comorbid condition that will appear as a byproduct of all the dysfunctionalities and dysregulations. This is a big review providing sufficient amount of data. But also, when you check for the myalgic encephalomyelitis chronic fatigue syndrome, you will see that one of the comorbid conditions that appears more frequent in under ME/CFS is also diabetes. In a recent paper in Nature that they analyzed for a big phenotyping study. One of the things that they indirectly are connecting with is also diabetes. And then it came in these ideas about the diabetes fatigue syndrome that it caught my attention. And I asked myself, maybe the modeling could be done not from the primary condition, so go for illness, ME/CFS, or long COVID, that would demand a lot of, I will put it this way, a lot of systems modeling because there's too many systems involved. But instead of that, let's try to start or doing that in parallel to simulate one of the secondary conditions that might tell us how the dysregulation start happening. And once you have this simulation done, you can attach this to a previous simulations, including neuroinflammation and many other things in the system modeling. So thinking about that direction, I went over all these conditions and I tried to find out what are symptoms that are common to all of them. And as you can see, fatigue across the board appear as one of the symptoms in all these conditions. And then there are all the symptoms that might appear in some conditions and do not appear in some other conditions. So, because fatigue is something that appears in all conditions, including diabetes, including Gulf War illness, post-traumatic stress disorder, and then you have problems that are related with metabolic syndrome. I said, okay, let's try to start from the simulation. The simple way is how we might get the imbalance between glucose, insulin, and the presence of diabetes, and how the diabetes might produce symptoms like fatigue or some other metabolic syndromes. I went, in that case, I took it the database that is related with the Gulf War illness data set. Is a data set from 55 patients with 116 different fields that were divided into demographic fields and questionnaires and biomedical variables. We're looking at the data set, disaggregating the data set between males and females, looking for a potential difference between biological sex. And this is what we were obtaining in the first approximation. We divided the data set based on TBI categories. First, using only 3 categories and looking at the BMI, how it is distributed between those categories in order to see if the BMI will be influencing the presence of traumatic brain injuries. And what we found is that the BMI, in principle, doesn't make any statistically significant difference on the appearance or the self-reporting of TBI categories, which means category 1 is no TBI reported, category 2, only 1 TBI event, category 3, 2 or more events. We disaggregated this a little bit more, reporting instead category 1 as 0 TBI, category 2, 1 TBI, 3, 2 TBI, and category 4, 3 or more TBI. As you can see between these two pictures, so the BMI didn't have too much effect on the self-reporting of the presence of those categories. I disaggregated the data also by females and males in both cases of categories for TBI, and the difference are statistically insignificant. However, when you look at the combination of post-traumatic stress disorder and TBI present, and I'm using here 2-digit, 0 means that the post-traumatic stress disorder is not present, And the second digit is the category of the TBI. Since I'm working with 4 categories of TBI, you will see here 0, 0, 1, 0, 2, 0, 3, and then here 1, 0, which means PTSD is present, but TBI is not present. Here, PTSD is present, and then you go to the second category of TBI. And we keep the BMI present over here. So as you can see, there are some differences that might be between no presence of TBI, no presence of TBI, and the presence of one reported TBI. Okay? When you compare the same thing on the other side, so you will see here presence of PTSD, but no TBI. And here you had it, no PTSD and no TBI. So there are not statistically significant difference between them because the range of variability, because of the small data set, is covering all of this. So in that sense, we eliminated the TBI as a primary cause of all the features that we were observing in the next slide. So the next slide is about the categories, but not by TBI. It's the categories by the C-reactive protein. And these are the typical classification encountered in the medical literature. When you have category 2 and category 3 for CRP, it means that you have minor inflammatory processes associated with conditions described over here. So now when you do the same thing with the BMI and those 5 categories for the CRP, you will start seeing that people in most of the cases are above the limit that is considered obese. And you see now an effect that even so is not really statistically significant, but it's marginally significant, that people with category 3, which mean some elevation in the value of CRP, are presenting a real inflammatory process. And when you do the same thing here for female, you can see that the effect is getting a little bit more clear. Okay, we're looking at the CRP, and we know that CRP is a marker of inflammation. Then we're looking at the IL-1 beta and IL-6 as 2 cytokines that are related with inflammatory process. And we compare the categories of CRP for those. Okay, the blue line, the green, and the red lines are the 3 ranges for the IL-1. So the normal level is from 0 to 5, the mild level 9 to 13, and the moderate 13 to 18. So most of the data about the IL beta 1 and the categories of CRP are pretty much in the area or in the range of having some mild inflammatory processes. So then we look it up at the associations of the blood pressure, glucose, cholesterol, with, in general, in the populations and with the insulin secretion. And looking at those results and the database that we came up additionally, where we included the age, sex, BMI, average blood pressure, total cholesterol, LDL, HDL, TSH hormone, glucose, and a factor that the people who reported that database, it means diabetes progression, which is an index telling you how many times in a year people get into the level of glucose that is considered diabetic. Okay, we working with that database, and we found that diabetes progression is correlating pretty well with the BMI. Actually, this is the strongest correlation. Also, it was correlating so well with the LTG, with glucose, and negative correlating with the HDL. Okay, if we go back to what we found in the Gulf War illness data set, we're gonna see that the BMI was present over there for a reason. It's because we got from this database that the BMI should be something to be considered because they are connected also with cholesterol or with the processing of free fatty acids. Keeping this in mind, we came up with the idea of generating a model where you have the input of the meals, and you might control the glucose level in your blood. And then you consider the glucose produced by the liver, the glucose consumed by the muscle, and the glucose into the adipose tissue. So we try to find out how the insulin feedback will control the production of glucose and reduce the level of glucose in the bloodstream, including the typical feedback between glucose and insulin, but also the presence of the growth hormones, the HPT excess, and the balance that you have between the liver and the production of free fatty acids. Mathematically, I didn't want to rediscover the water, and I did a literature search what has been done for the mathematics of modeling diabetes. And based on this 6 paper, we got some ideas how to process the representation of the glucose insulin feedback. So the variation of the glucose over time is controlled by the average input of glucose from the liver, the muscle, and the adipose tissues that is reconverting fat into glucose. Then you have the effect of the thyroxine 4. Here is the free fatty contribution to the production of glucose. And then the last 2 terms is how the glucose is eliminated by the insulin, where here is the sensitivity, the insulin sensitivity factor, and here is the natural degradation of glucose. The insulin variation over time is used, it has been described using Michaelis-Menten or Hill type function, where the glucose is exerting a saturation effect on of how much insulin is produced, but that number of how much insulin is produced is directly proportional to the number of beta cells that are activated times a function that describes the effect of the HPT excess. Likewise, the insulin production is proportional to a saturation effect due to the free fatty acid and the natural degradation of the insulin. The beta cells are, I would say, are induced to work due to the glucose levels, the HPT axis operation, which in this case, instead of being a linear function, will become a quadratic function, because depending on the level of the thyroid hormone you have, you might have a situation when the thyroid hormone will facilitate the or activate the beta cells, and sometimes they will inhibit. And the point of inflection is going to be controlled by the threshold value U. Then we have the equation for the free fatty acid, the growth hormones, and the two equations representing the HPT axis. And the idea is just that when you got pancreatic beta cell release insulin, that insulin will control the glucose level, and the system should go back to the homeostatic equilibrium. So the result that we get, the time here is in days. We got a transient behavior of a glucose, and then the glucose tend to be at the level that typically you find in the blood concentration. So what happened here? If you want to see a departure of glucose towards diabetes, you need to create an imbalance in your system. Since we didn't include any imbalance yet, because we're trying to reproduce the homeostatic equilibrium, so you will see after the first transient behavior, which means that you will see a variability due to the mathematical representation, but then after the first group of days that you have here, so glucose is stabilized at the normal level. What happened with the insulin is a little bit different here. And this is one of the problems that we're facing with the problem, with the model. According to the model, we're obtaining here a behavior of insulin that doesn't correspond so well with what we have found in the literature, because the peak of insulin here is happening well behind when the peak of glucose is happening, even so that the insulin, when it returns back, it doesn't return to the typical initial condition we initiated that simulation. One of the things that we consider that will be the source of this weird behavior is the poor calibration, because we don't have enough data to compare the model with, and from there obtain the rate of reactions that are present in that model. The same thing that you see with insulin is happening with the beta cells. So for the thyroid gland and the free fatty acid, we didn't find too much trouble in getting into the homeostatic equilibrium, but insulin and beta cells are, for us, one of the most difficult things because we couldn't find yet a very decent data set that would allow us to create a good rate of reactions. So comparing with the modeling that we have done now, we're missing the calibration with experimental measurements for the reaction constant. So any data set available that include information about metabolic panels, thyroid hormones, cortisols will be really appreciated, because it will help to improve the model. So the joint work of alpha and beta cells and insulin will be included in the new extension of the model, and the simulation, including the modulation from the HPT axis and the effect of insulin resistance backward on the HPT is something that we're looking for. However, we know the effect of the HPT on the insulin, but the effect of insulin over the HPT is not very clear. Likewise, it happened with the effect of cortisol and the effect of the HPG axis. This is something that I was looking for in the literature, and there is not a consensus how the last three things are happening. However, when you look at the data originally that I presented, you saw that there is a disaggregation between male and female, and the presence of diabetes in the Gulf War illness is more common in females rather than in male. So meaning that the inclusion of the HPG axis will be something important. And here in those pictures are the pictures taken from different literature search that we have done about the potential inclusion of cortisol and the thyroid hormone, how they might affect beta and alpha cells. About the last three things, I'm not very confident yet, and I will be more than happy to listen feedback. How should I include those things? Whether they will be positive or negative feedback, or whether those feedback will be sensitive to some kind of threshold values, because I'm a little bit lost about these three pieces over here to move ahead the simulation. So as what we have done as of today, I want to recognize the work of Sandeep Dronavali. He's an undergraduate student from the Department of Biology. He carried out most of the statistical work that we did with the second database. And in that statistical work, he was able to find the principal components that are predictors that are very robust to see the progression of the diabetes. And he was very helpful in the implementation of the mathematical model and testing the mathematical model on Python. So I run the mathematical model on the software Mathematica, and the student run the same model on Python. Why we run it on two different computer languages? It's just to find for the stability and the reproducibility of the results. And in both cases, we're getting the same type of graph, meaning that the numerical method that we're using were the one that are correct, and it's not a numerical error that we're getting, it's more a conceptual error in representing the feedback mechanism. So that's what I wanted to present, because this is not a final presentation. It's more about the progress and asking for help.